Hello everyone. In today's lecture, we are going to understand the concept of differentiation in a little more depth than in the last lecture. Now, as you already know, in the last lecture, we came across the slope of or the gradient of a straight line, and we said that the slope of a straight line is the difference of the y coordinates to the difference of the x coordinates, right? Now, please remember, in this case, the points are A, x1, y1, B, x2, y2. Okay, so we can say the slope of the line is y2 minus y1 upon x2 minus x1, or x1 minus x2, y1 minus y2 upon x1 minus x2. We can also say m of AB is y1 minus y2 upon x1 minus x2. This is also perfectly right, okay, where we take the point B as the origin and A as the second point, okay. But this is not correct. If we write something like this, y1 minus y2 upon x2 minus x1, this is not acceptable, okay. So please bear that in mind. So for the moment, now we will take this concept of the straight line. We also came across the concept of the limits, and the third one is that the tangent at any point, the gradient of the tangent at any point on the curve is what we are going to find out, okay. If there is a curve, and if you want to find out the gradient of that curve at a certain point, it is nothing but the slope of the tangent at that point P, let's say x and y. This is what we came across in the last lecture. So now we are going to use these concepts now in going into the concept of differentiation a little bit further. So let's say this is the x-axis and this is the y-axis. Let's draw a curve, okay, and let's have a point here P, which is denoted by x and y. So this is the x, this is the origin, this is y, so this is x and this is y, this point is x and y. Now let's take a point, another point Q. Let's take a point Q which is a little bit away from P and at a distance of delta x and delta y. So this delta x and delta y are very, very small amounts, or infinitesimal small amounts away from P. So delta x, you can say, is extremely small, so that Q is very close to P. But this is a magnified view of the situation, okay. So this delta x and this delta y, this is away from, this is a point Q. So this one is x plus delta x, and so the coordinates of Q are x plus delta x and y plus delta y, where delta x and delta y are very, very extremely small amounts, okay. So if we have this one here, the point Q, so this is y plus delta y. So now, as you see, if we join these two, this is a straight line PQ. But since Q is very close to P, you can say that the line PQ is almost the same as the tangent at the point P. How is it? Let's do it here. This is the curve. Let's say we have a point P here, we have a point Q here. So now this is the line PQ. Now as you can see from this one, we want the gradient of this tangent. But if we join P and Q, this is the line PQ. Now the slope of the line PQ is not the same as the slope of this line of this tangent. But now if we take this Q a little bit closer. Let's say this is Q1 and we again join these two lines. Now you will see that the slope is a little bit closer. Now if we join P and Q1, you will see that this line is nearly now approaching this line. Let's take a point here, Q2. If we join this line, you'll again see that this line is still closer to this line than this line and the PQ line. So as we move Q towards the point P, this line is approaching more and more towards the tangent at the point P, and we can definitely say that the limiting value of this is equal to the tangent at the point P. So now since we have defined these two quantities delta x and delta y to be very small amounts, so that point Q is very close to the P, we can say that as Q approaches P, or as this is delta x, this is delta x, or as delta x tends towards 0. So if delta x tends towards 0, so that Q is very close to P, we can say that this is almost the same as the tangent at the line at the point P. Okay, so how do we write it? Okay, so we can say that gradient of PQ. Now PQ is a straight line, so we can apply the concept of the gradient of a straight line is equal to y2 minus y1 upon x2 minus x1. What is this? Is y, this is x2 and this is y2 and this is x1 we can say, and this is y1. So we will say it is y plus delta y plus delta y minus y1 is what here? It is y. Okay, because we have taken it as x and y. Okay, and this is x, so this is x2 and y1, and this is x1 and y1. Sorry. So what is x2? X2 here is x plus delta x minus x1 here is x. So it is y plus delta y minus y upon x plus delta x minus x. This y and this y will cancel, x and x will cancel, so we are left with delta y and delta x. So we have here the slope of PQ is delta y by delta x. So as delta x approaches 0, this will approximate to the gradient of the tangent at a point. So this is written as, therefore the limiting value of delta y by delta x is equal to the gradient of the tangent at P, and this is written as limit of delta x tends to 0, because delta x is, if it tending to 0, this is the limiting value, and that is the so this limiting value is called the differential coefficient, or also known as the first derivative of y with respect to x. Okay, and it is also denoted by dy by dx. This is denoted by dy by dx. Okay, so the process of finding out this limiting value is called differentiation. Okay, this process is called differentiation, the process of finding out this limiting value. Now please note, dy by dx means derivative of y with respect to x, or we can also say differential of y with respect to x. Okay, also means that dx is an operator that is operating on the function y, where y is equal to any function of x. It also means this is an operator. This is an operator that is operating on y. That's y is a function where y is a function of x. So ddx is also known as an operator. And we can write this as ddx of y. Okay. So this is the concept of differentiation, and now we will take we'll be taking differentiation of some simple algebraic functions so that we can arrive at the formula for the differentiation of a algebraic expression. So let's take a function y is equal to x, and as you know, y equal to x is nothing but a straight line. It's not a curve. But let's see what we get. Now we already know that the slope of a straight line is a constant, right? So let's see if we get the same thing by the process of differentiation. So now let us differentiate this one. Okay, so we will draw this one. Let's say y equal to x is still we can take this as x is a curve, let's say, for the instant. Okay, so we will take a point P, we'll take a point x and y, and a point Q, which is x plus delta x and y plus delta y. Okay, so let's take this one. So this is delta y and this is delta x. Now since y is equal to x plus delta x, this is also equal to x, and this is also equal to x plus delta x. Okay, so we can say now that the slope at this point P is equal to dy by dx, as we had done in the last before, and this is the limiting value of delta x tends to 0 of, now since y plus delta y is x plus delta x minus x, and again x2 minus x1 is x plus delta x minus x. So we are getting delta x by delta x, which is a constant, and which is equal to 1. So whatever y equal to x is, we now know that the slope will always be equal to 1, and 1 is a constant. Suppose if we had y is equal to 2x, that is also a straight line, so the slope would have been 2. If we had 6x, this slope would have been equal to 6. Okay, so this is how you get the slope of, or the gradient of, the curve at a point P, that is the gradient of the tangent at that point P. Okay, so in the next lecture I'll be taking some more examples of higher powers of x to come to a formula for differentiation. Till then, thanks for watching. Meet you in the next lecture.